Good afternoon, and thanks for your time to give us the opportunity to interview you. We are going to interview Josh Frieman. You are director of the DES project, and is the dark energy survey, the new approach to the structure of the universe we are trying to understand. Thank you very much for being with us. The first thing I would like to ask you is about dark energy. That is what is giving name to the project. What is that dark energy, and why are we looking for it?
Okay, so dark energy is the name we use for what we think is causing the universe to speed up. So if we go back in history a little bit, we've known for since the 1920s that the universe is expanding. Most galaxies that we see out in the universe are moving away from us. And they're also moving away from each other. So the universe is expanding. But we expected that over time, as the universe expanded, it would slow down because galaxies over here are pulling on galaxies over here due to gravity. So we expected that as the universe expanded, it would slow. But what was discovered about 20 years ago is that the universe isn't slowing down, it's speeding up, it's getting faster. And so we now know that the universe expansion has been speeding up for about the last 7 billion years or so. For the first 7 billion years of the universe, it was slowing down, but then it started speeding up. This doesn't happen under our normal understanding of gravity, so we have to invent a new substance which would have the property that instead of making things attract, it would make them repel each other. And that's what we call dark energy. It's something that would be filling the entire universe. We now know it would make about 70%, so nearly 3/4 of all the energy in the universe. And it has the property that it would cause galaxies to repel each other rather than attract, and therefore cause the universe to speed up. But beyond that, we really don't know very much about it. There is one particular concept for what dark energy could be, which goes back to Albert Einstein. He first made his theory of general relativity in the 1916. He introduced something called the cosmological constant into his theory, which was really the first example of what we now call dark energy. We still don't know if dark energy is the cosmological constant, or if it's something else, and that's what the Dark Energy Survey is trying to find out.
The name of the project is Dark Energy Survey, but you really are looking for matter, dark matter and magnetic matter, together with light, and using light to detect that kind of matter. What is the relationship between matter, light, and dark energy?
Good. Yeah, that's a good question. So, dark energy is this thing causing the universe to speed up. What we want to do is try to figure out what its properties are. And we have kind of two things that we can do that we can try to measure, which are the effects of dark energy on the universe. So one thing it does is, as I said, it speeds up the expansion of the universe. So one thing we can try to do is measure how fast is the universe expanding today, how fast was it expanding in the past as we go billions of years into the past. And dark energy, because it's pushing things apart, will change that history of the cosmic expansion. The second thing we can try to measure is the growth of structure within the universe. So we have this picture that the early universe was relatively homogeneous, relatively smooth. The density of matter over here was pretty much the same as it is over here, but as the universe evolved, it got lumpier with time because of gravity, and eventually these structures formed the galaxies and larger scale structures. But again, we know now that dark energy is trying to pull those structures apart, and so there's this competition between the gravity of dark matter forming structure and the repulsive nature of dark energy pushing it apart. So if we can measure that history of the growth of structure in the universe, we can also get a handle on on the properties of dark energy. So we have these two things we're trying to do with the dark energy survey, is the expansion history of the universe and the history of the growth of structure. How do we measure those two things? Well, there are a variety of ways to do it. For example, we can measure the expansion history by looking at distant objects like supernovae. These are exploding stars, and seeing how bright they are at different times in the past. That gives us one measure of the history of the expansion. So there we're using light from these supernovae, and we're using them as kind of signposts to tell us about the history of the expansion. For the growth of structure, again, dark energy, we can't see it. We don't think it clumps together itself, but it impacts the evolution of structure. And so what we can do here, for example, is look at galaxies, see how clumped together they are in the universe today, and looking back in time. So we can trace the evolution of structure in the universe. And that structure is mostly made of dark matter, but we can see those structures because the dark matter has within it these luminous galaxies. So those are examples of some of the things we're trying to measure: the clustering of galaxies, the supernovae. But we're really trying to get at this more fundamental questions of the expansion history and the growth of structure.
Taking different perspectives to
Right.
integrate them and
Exactly.
try to have a new picture of it.
Yes.
Okay. Okay. My next question is about dark energy. Is supposed that it affects the structure of this in space-time. It's not a repulsive force, but it's an intrinsic property of the space-time.
It could be. So it depends on the theory. So, for example, let's go back to Einstein. He introduced this cosmological constant, which he thought of as actually a new constant of nature, in addition to all the other ones we know about, the strength of gravity, the speed of light, etc. But we then reinterpreted that in the 1930s, 1920s, was reinterpreted not necessarily as a new constant of nature, but actually as something fundamental about space-time. Namely, it's the energy associated with empty space. So imagine we take this cup here. Suppose I could attach, I could seal it off, attach a vacuum hose, get rid of all the atoms, all the air inside it, shield it from, cosmic rays and everything, so that it was really truly empty. It would have no matter, no particles in it. Well, according to our classical understanding of physics, if there are no particles in there, then there's no energy in there. But according to quantum mechanics, even if there are no particles in there that I can measure, there's still an energy there associated with the kind of fundamental uncertainties.
Fluctuations,
quantum fluctuations. Exactly, quantum fluctuations. Those carry energy, and the energy carried by quantum fluctuations, that's the energy of empty space. There's no particles. And that is exactly what a cosmological constant looks like. So it could be that what's driving the universe apart is simply the energy of empty space, sometimes called vacuum energy, or alternatively, the cosmological constant. And in that case, you're right, dark energy would be a kind of intrinsic property of space. There are, however, other theoretical ideas that perhaps dark energy is associated, say, with a new particle, a very light particle that could be kind of a distant cousin of the Higgs boson that was discovered a few years ago at CERN. So there are theories like that, in which case it wouldn't necessarily be an intrinsic property of space and time, but it would be a signature of some new fundamental particle or new field in the universe. And so those differences, those different ideas lead to different predictions for what we would see in the dark energy.
The scale you are exploring.
Exactly.
Okay. Very, very interesting. According to this, and related to it, is baryon acoustic oscillations that you are using to explore that big structure in the galaxies and the supra-galaxy structures. And what are the baryon oscillation and acoustic oscillation?
Good.
In a light way.
Okay, sure.
If possible.
Yeah. So basically, baryon acoustic oscillations are similar to sound waves that we're familiar with. And essentially what happens is early in the universe, around 400,000 years after the Big Bang, the universe was filled with baryons, say protons and electrons, and also photons from the cosmic, what today is the cosmic microwave background. These particles were all zipping around, they were all colliding with each other. And on top of that, you had fluctuations in the density of the universe. So you had regions where you had a little bit more baryons than average, others where there was a little bit less. Where there's more baryons, there's more gravity, it would start to shrink, so to collapse under the action of gravity. But because at this early time the baryons were scattering with the photons from the microwave background, photons, light, exerts a pressure. And so the baryons wanted to collapse, the photon pressure was resisting that collapse, and that competition sets up a sound waves, a sort of an oscillatory behavior. And those sound waves get imprinted both in the microwave background, which has been measured by the Planck satellite, and it also gets imprinted as fluctuations in the density of baryons and dark matter, which we can see in galaxy surveys. So really, baryon acoustic oscillations are these sound waves that get set up in the very early universe that we've now seen directly both in the microwave background and in a much more subtle way in the spatial distribution of galaxies.
So you are looking for that special distribution of matter and dark matter and baryon matter to try to understand that process in the first time of the
Right. Yeah, so we use baryon acoustic oscillations as one of several probes to try to understand dark energy. And essentially what happens with this particular probe is these sound waves, which get set up early in the universe, they can travel a certain distance. And that distance therefore gives us a kind of a standard ruler, a standard length, against which we can compare the spatial clustering of galaxies today. And by doing that comparison, that gives us information on the expansion history and therefore on dark energy.
So it would be another different ruler to make some measures in the primitive universe, and to take different conclusions about it. As you have been using supernovas and so on, and microwaves, and now you are using this kind of approach. It's more a statistical approach, I think so.
Yes, exactly. Right. So with a supernova, we call those standard candles. Those are objects which all have more or less the same intrinsic brightness. And so by seeing how bright they appear to you, you can tell how far away they are, just like the headlights of a car. With the baryon acoustic oscillations, it's not as if we really have this ruler, out there in the universe, but instead, as you said, it's a statistical phenomena. There's a slight excess probability for two galaxies to be separated by a few hundred million light years from each other. And we can measure that excess probability now with galaxy surveys and use it in the same kind of way.
Very interesting. Where to look for this kind of structures, and what are they adding to the model, to the current model of cosmology? Why are we using this new approach, using baryon acoustic oscillation, and what are they going to add to the current model?
Okay, good. Yeah, so I think so baryon acoustic oscillations, like the supernovae, are really good at telling us about this history of cosmic expansion. And it's simply kind of another tool in our toolkit. And the baryon acoustic oscillations are particularly useful for measuring the expansion history as we go further and further back in time. So the supernovae are quite good at getting us, back about 7 billion years into the past. We expect that the baryon acoustic oscillations will be they're good in that interval, but also we think they'll be very helpful in enabling us to push even further back in time to measure the history of the cosmic expansion.
How this project is making possible to measure these properties, and what's the special issues you are facing with the project? Right.
Okay. Good. So what are we doing in DES, in the Dark Energy Survey? We have a big camera. It's about this big around. It's about as long as this table. It's on a big telescope in Chile, and what we're really doing with it is just taking pictures. Every night we go out and we point the telescope at different places, take a picture, we expose for about 90 seconds. We use different colored filters so we can get color information. And then we just move around over the sky so that after 5 years we'll have covered about 1/8 of the entire sky. So what does that give us? It gives us images for a few hundred million galaxies, and also tells us their colors, so we can get an idea of how far away they are. And then we can use those data to do things like look at these baryon acoustic oscillations by measuring how the galaxies are clustered with respect to each other. So we figure out, we have to detect the galaxies in the images, figure out how bright they are, how far away they are, and then we use these statistical methods to figure out how clumped together they are. That's one technique. A second technique is galaxies are not just randomly distributed in space, they tend to clump together. And occasionally you get many galaxies in a relatively small volume of space. Those are called clusters of galaxies. And those are very easy to identify because you see many galaxies in a small part of your image. So we can identify clusters of galaxies, and we can just do a census. We can count the clusters in different distances from us, or different times back in the past. And by counting how many clusters we see now, 2 billion years ago, 4 billion, 6, 8 billion years ago, the number of clusters that we see is again a reflection of this fight between the gravity of dark matter pulling things together to form the clusters and the repulsion of dark energy pushing them apart. So that's another technique. A third technique is when we measure these hundreds of millions of galaxies, we not only measure where they are, we can measure the shape of the galaxy, how it appears to us on the sky. And those shapes are slightly distorted because the light from these distant galaxies, as it travels to us, gets bent because there's matter between us and those galaxies, and the gravity of that matter will curve the path of the phase. So that leads to a slight distortion, or what we call shearing, of the galaxy images. We can measure that, and again, in a statistical way, correlate those shapes of galaxies with each other, and that tells us about, primarily about the growth of structure, it's that structure which is bending the light. So these are a few of the techniques that we can use, but they all go back to basically taking pictures and analyzing those pictures. So it's just like, with your phone, if you could take many pictures all around Benasque, you could then analyze those pictures to learn about who lives in Benasque, what kind of people they are, what kind of houses they live in. So it's very much the same kind of thing. It goes back to the pictures, and then we're extracting this information about the universe from these images.
The light we receive.
Exactly.
That's very interesting. And going on with that line, you have just made public the first results, the first fine results once analyzed and so, just 2 hours ago.
Right.
And we would like to know what you have found.
Okay, good. So basically what we just released was results from the first year of our data. So DS is a survey being done over 5 years. We're now, in 2 weeks, we're going to start our 5th season. So here we're just analyzing a portion of our data so far from the first year. And basically what the 2 things we can measure most precisely with the first year of data is how much dark matter there is in the universe, excuse me, and also how clumpy that dark matter distribution is, or how clumpy the mass is on large scale. That is it relatively smooth like the surface of this table, or is it more lumpy? And those are 2 important properties of the universe that are part of our general picture of cosmology. And so we've made very precise measurements of those things, and the interesting thing is that we can now compare those results with measurements of the cosmic microwave background from the Planck satellite, which was looking at the same kinds of things, but in the early universe, when the universe was only 400,000 years old, and it was much, much smoother, much less lumpy then. And the Planck measurements of the universe, its picture of the universe at that time, gives us a prediction for precisely what we should see today in terms of how much dark matter there should be and how clumpy or lumpy the universe should be. And what we find is that our results are very close to what the Planck satellite predicted. They're not exactly in agreement, but they are statistically consistent with them. And that's quite amazing because we're taking this prediction based on an observation of the universe, 14 billion years ago. We can now calculate exactly what it should look like today, and what we see is almost what we predicted in this very simple model of how the universe evolves. And the interesting thing is not only do they nearly agree, but the accuracy of our measurements today are now comparable to what the microwave background accuracy is from the Planck satellite. So it's for many years, the observations of the microwave background have been the most accurate observations we've had of the universe. But now with DES and other surveys that will come after it, Galaxy surveys are now getting to that same level of accuracy. So we can really compare these 2 observations
in different
times, really see if they're consistent, and really start to probe the model in much greater detail than we've been able to do before.
And according to this, is it possible to discriminate which kind of theories you are managing are correct and which one are not going to be correct anymore?
Yeah, so I would say we're still in the early phase of this. We can already exclude a number of theories, and the data we see, say for dark energy, are consistent with this model we talked about before, where the dark energy is this property of space-time. It's the energy of empty space, or Einstein's cosmological constant. That model is completely consistent with the data we have now. It'll be interesting to see in the next few years, as we analyze more of our data, if that model will still be consistent with the data. So far, it looks great. And so that's suggesting Einstein was right. But we'll have to tell with more data in the future whether that model still survives the tests.
Are we accelerating according to the results? Are we slowing down?
So according to our measurements, the universe is speeding up. It's accelerating.
Speeding up. Clearly it's speeding up. I'm going on to the this data. Okay, about your work, your daily work in the project. We would like to know more about your responsibilities like director of the project, and to have a more clear idea of how complex is your work.
Oh, okay. Right. That's a good question. Yeah, I've been director of the project for 7 years. I was one of the people who kind of started the project back in 2003, so it's been going for quite a while. And it's been interesting to see the evolution of the project. You know, we were just a few people sitting around a table like this saying, yes, we should build a camera and do this survey. And whereas today we now have about 400 scientists from 26 institutions in 7 countries, all around the world, who are working on this project. And that's quite exciting to see that. And so my role as director is to keep the project going, to make sure all the different pieces are smoothly working together, and really to kind of manage the different areas of the project. So the bulk of our effort now is scientists, mostly young scientists, working with the data, analyzing the data, getting out science results. But then we have people who operate, they operate the telescope and the camera. We work with the Cerro Tololo Inter-American Observatory on that. And we supply people there to go down to Chile and observe with the telescope to take the data. We then have teams of people, mostly in Illinois, at the University of Illinois, who are processing the data. So they take images from the camera and process those images.
The statistical analysis of the
to enable the statistical analysis. So they, the images that come, so in your camera, you have different formats. You have, the RAW format, you have JPEG. So the images we get out from our camera, they're always in RAW format.
Sure.
And we have to process those, not to make JPEGs, but to make images where we've removed artifacts due to the camera or the telescope. So that involves a lot of heavy computation. So we have a team of people there, and they have to, talk with the people, keeping the camera going, and with the scientists who are using those images for science. And so much of my job now is basically coordination, making sure the different groups are talking to each other, making sure we have support for the project to keep it going, to take the data, to analyze and process the data. So it's interesting because scientists all have their own very strong opinions about the way things should be done. And science tends to be very non-hierarchical. It's not like a corporation where you have your boss and then their boss and then their boss.
More plain.
It's more planar, it's more interactive, it's more based on consensus. And so a lot of my job is working to develop consensus. So facilitate, or to when we want to maybe change direction or do something new, build a consensus, make sure everyone is comfortable with that, thinks it's a good idea. So that's much of what my role has evolved into over the last years.
And do you have still time to make science? Because I think it's not easy to
it's not easy.
Do it with so much.
That's a real challenge. So much of my science I do in collaboration with students and postdocs working at my institution and other institutions. So it's the way I do science is different from when I was younger. I would do a calculation. Now it's more saying, oh, why don't you do this calculation and then let's talk about the findings, and okay, that doesn't look right, let's try this. And so it's at somewhat of a remove. but it's still connected. So it's still participating, but in a different way. And yeah, that's always the challenge with these kinds of projects, because they do require a lot of coordination, and that does leave very little time, at least for me, to really dig into the data myself.
I suppose that this kind of meetings here you are now having in Benasque is a good space for you to reconnect with scientific.
Yeah, we have quite a number of people from the collaboration for the meeting here this week, and it's been very good to get people together to talk about these things.
Okay, I have no more questions. It's really a pleasure to have the opportunity to talk with you, and thank you very much for your time, and good luck in the future with the experiment and the project.
Great,
Thank you very much.
Yeah, thank you.
Okay.